Okay, so now we're going to look at actually doing or solving some differential equations. We are asked to use integration to solve the differential equation. We're not verifying. We'll review that in just a minute here. But we want to just use integration to solve the differential equation. The way we approach these problems is very important to pay attention to, because this is what we're doing in the majority of this chapter. We'll be solving differential equations. The main thing we do in Chapter 6 is solving a differential equation, and we just keep building on the different methods of how we do that. So in a differential equation, you are given a derivative, something that is a derivative. You can tell because it's got dy over dx or y prime. And you are asked to find y, or the function that it came from. If this is the derivative, the function it came from is called y. So the first thing we do is we write down we're looking for y. Well, how do I find y? To go backwards from the derivative to y, I take the antiderivative or integral of basically both sides. That's really all I'm doing. The integral of this side and the integral of this side. Okay? The integral of dy over dx is y. The integral of this side I have to calculate. Remember, the dx in an integral is really just, it's very important for substitution. It allows us to do our substitutions correctly. Think of it this way: you're just multiplying both sides by dx, and you had the derivative of y, you took its antiderivative, it's y. Alright, so to find this derivative, antiderivative, I'm going to find u, which is 1 plus x squared. Du is 2x dx. Substitute back in, y equals, the x dx is going to be replaced with 1/2 du, and this is u. So I end up with the antiderivative of du over u, that happens to be natural log of u with a 1/2 in front of it. And remember, we always use that absolute value, plus c. Put the u back in, and I will have solved my differential equation. And there's my final answer. The plus c is very important. Alright, the next one is exactly the same. The antiderivative of dy over dx is y. I need to find the integral of x radical x minus 3 dx. I'm going to use some substitution here. U is x minus 3. Du is just dx, and I know in the past, if you took Calc 1 for me, you know that dx is not a good du, but it's going to work here. I'm going to use the substitution. This x I'm not sure what to do with, so I'm going to leave it. I know that x minus 3 is u, and that's going to be to the 1/2 power, and the dx becomes du. Now I can easily switch out this x using this equation. I know that x is u plus 3, so I can rewrite this now as the integral of u plus 3 times u to the 1/2 du. I can then distribute that. When I multiply u times u to the 1/2, I add the exponents and get u to the 3/2 plus 3u to the 1/2. And now the antiderivative is very simple. It's a power rule. I add 1 to the exponent and divide by the new exponent, multiply by the reciprocal. Add 1 to the exponent and divide by that. The 3's will cancel, and I'll have a 2. And then the very last thing that I need to do is put my u's back in, so y will equal 2/5 times x minus 3 to the 5/2 power plus 2 times x minus 3 to the 3/2 power plus c. And I'm all done. So that's really how we're going to be solving a lot of differential equations for the rest of this chapter. And I thought we would just go back and review a couple of problems from what we talked about before. So I'm going to switch screens real fast here, and we're going to take a look at Calculus 8th edition. The first thing we're going to look at is problem number 33, and it says verify that the general solution satisfies the differential equation. Then find the particular solution that satisfies the initial condition. Remember that a particular solution is one that you find the c's. So that's what we're doing when we find the c's. So our problem here, we know that y equals c1 times the sine of 3x plus c2 cosine of 3x. And we want to see if it matches this differential if it is a solution to this differential equation. So this is the differential equation we want to match it up to by taking the derivative. We also know that y equals 2 when x equals pi over 6, and that y prime is 1 when x equals pi over 6. So we'll worry about those as we go. So the first thing, I notice my differential equation has a second derivative in it. So I know I'm going to have to work backwards 2 derivatives, and that's the one I need to make look like this and then test my initial conditions. So first of all, y, the antiderivative, or the derivative, sorry, of y. The derivative of the sine of 3x is going to be 3c1 cosine of 3x. The derivative of c2 cosine of 3x is going to be negative 3c2 sine of 3x. So for my second derivative, the derivative of cosine of 3x is negative sine of 3x times the derivative of 3x using the chain rule. So that 3 will be multiplied by the 3 here. I'll get negative 9c1 sine of 3x. The derivative of sine of 3x is going to be 3 cosine of 3x, so that'll make that negative 9c2 cosine of 3x. So now I need to take this and see if I can manipulate it and make it look like that. So first of all, I notice that my differential equation is equal to 0. So I'm going to take my second derivative, I'm going to get it equal to 0. And what I notice, I'm basically going to be adding both of these to the other side. I notice they both have a 9. I'm going to factor that 9 out. It's going to become plus 9 times c1 sine of 3x minus, or plus then, c2 cosine of 3x. And that's going to equal 0. So now I almost have it. I've got the y prime plus 9, and now is this indeed the y that I started with? And it looks to me like it matches up exactly, so I can write this as y prime prime plus 9, y equals 0. So this matches up. So that is verified, it's good. So now I just need to see that the first derivative was 1 when x was pi over 6, and that that y is 2 when x is pi over 6. So really this is easy. I can use this to verify that one, and this to verify that one. Another thing I could do is plug in my C1 and C2, or try to find those, but we'll do this the other way. So y is 2 when x is pi over 6. So if I put pi over 6 in here, I've got 3 times, let's see, 3 times pi over 6, I will have the sine of pi over 2 plus c2 times the cosine of pi over 2, and that should equal 2. And then I should also have the case where the first derivative is 1 when x is pi over 6. So that would be the cosine of pi over 2 minus 3c2 times the sine of pi over 2. So let's see, sine of pi over 2 is up here. Cosine is 0, sine is 1, so that'll be 1 times c1, or just c1, plus cosine of pi over 2 is 0, so that'll be 0, so I'll have that c1 equals 2. So from there I know that c1 equals 2. And then from here I'll have, well, the cosine of pi over 2 is 0, and the sine of pi over 2 is 1, so I'll have negative 3 c2 equals 1, so c2 is negative 1/3. So with those initial conditions, I not only verify that it's a solution, but I can also find the constants. Alright, so finally number 23 is just another problem where we're trying to determine if it's a solution to a differential equation. So we're going to take a look real fast at number 23. We're given y equals the natural log of x, and we are asked to, this is my solution, and my my differential equation is xy prime minus 2y equals x cubed e to the x. And this time I want to see, is this a valid solution to this differential equation? It's a yes or no question. And so I'm going to find the derivative of this, and I only need to find one derivative because this only involves, sorry, let me back up a bit. I need to find the derivative of this, see if I can rearrange it and manipulate it to look like this. So the derivative of natural log of x is 1 over x. Now I somehow need to make it look like this. So let's just try, we did another example like this. I noticed that my y prime has an x. So if I multiply both sides of this by x, I'll have xy prime equals 1. And then I know that I would need to subtract 2y from both sides. So I can do that. I can do that to both sides. So I'll have xy prime minus 2y equals 1 minus 2y. And y is the natural log of x. Over here, I guess I have to think, is there any way I can make that look like that? And I don't really think there is. And so I would say that this is not a solution to this differential equation. And sometimes that's the case. They're not always asking you to verify, sometimes just see if it is yes or no. So that should cover the first part of section 6.1. We're also going to be talking about slope fields and Euler's method. Euler's method. And those are parts of the Calc A/B test, and we'll cover those later.